Yeah, we're having a very bad. Hello and welcome back to Calculus 1 this glorious Sunday morning.
Saturday.
Oh, it's Saturday?
Saturday.
All right.
It's not morning either.
And it's not morning either?
No.
Oh, it passed 12. Okay,
Yeah,
great.
it's noon.
So restart.
Okay. I'm ready.
Hi, it's Calculus 1, section 4.4 optimization problems. We are going to take a look at application of minima and maxima. Therefore, what you learned in section 4.1 on how to find min and max is how we are working these problems out. We are adding the component where we model. So these are word problems. We make our equations and then go on. These problems will be upgraded to something called Lagrange multipliers in Calc 3, where you will have more variables, more equations, and some kind of multidimensional generalized method to solve these problems. So for now, basic two-dimensional approach, and we can start with a word problem that says find two numbers x and y such that x plus y is 10 and x squared y is the max. This will always be the case, whether those equations are spelled out to you or just bluntly given to you. You have two equations with two unknown variables. And one equation is called objective equation. Because that's what the point of the problem is. You want this product to be maximum. You want profit to be maximum. You want cost to be minimum. You want your energy used to be minimum and so on. So you have objective equation. And then you have constraints, right? You want to keep the profit up but keep the cost down, right? So this one over here is called constraint. And your success in these word problems will really play at whether you are able to recognize these and write these formulas out. That's it. The rest is the joke. You have two equations, x plus y equals to 10, and you have equation x squared y equals a max. You will solve and plug in for, let's say, x equals y minus 10, right? Or sorry, 10 minus y. So x is equal to 10 minus y, and you will plug in. So what you get is 10 minus y times y is equal to a max. And when you FOIL this, well, distribute whatever you need to do.
Minus y squared.
That's what I said. Right? Equals a max. So now when you look at this max value is some number that you don't know, right? What I'm going to do is I'm going to take derivative in respect to y, in this case, because that's the variable that I have. I'm looking for the max of this, right? So you take the derivative. Now observe what happens. You get 10 minus 2y is equal to 0, because max is some constant number with emphasis on the word constant, which means when you take a derivative of the word max, which is a number, it's going to be 0. What happened?
No. It's 10 minus y squared, not 10 minus y times y. So you're substituting 10 minus y to x and x is squared in the max problem.
What?
And
Oh, there's this one. Ugh, okay. Fine.
I'm glad that I wasn't the only one.
Fine. Just, yeah, so that's 100 minus 20. So we have 100 minus 20y plus y squared times y equals mx. Holy nightmare. So that's 100y minus 20y squared plus y cubed equals mx. There we go. And then we take the derivative. There's a square there. It was hiding in plain sight. All right. So now when I take the derivative, I get 100 minus 40y minus 3y squared equals to 0. So this max turns into a 0. And look how great math works over here.
Isn't that a plus 3y squared?
It is. Look.
That's what he said.
It's, look, plus. See? Plus 3y squared. What's the problem? Of course.
They just don't know.
So we know that when we are looking for min and a max, the horizontal line slope is 0, right? Which is the reason why we used to set derivative equal to 0. But now when you find the derivative, it will automatically be equal to 0 because this max or a min is a constant number whose derivative is 0. So you see how all the concepts work together. So that's the only theory behind all of this. You find the equation and you differentiate it, the word min or a max will immediately become 0, so that's derivative equal to 0, and you are looking for min or a max. All right, so now you grind this through your quadratic formula, and you will find the value for y. Now, whether it's, well, we'll see. So what do we have? We have negative b plus minus b squared, which is that, minus 4ac, which is that, divided by 2a, which is this, which is 40 plus minus, that's 400, that's 20, divided by 6, so we get 60 over 6, which is 10, or we get 20 over 6, which is something else. Well, 20 over 6, that's 10/3. So x is one of these two values. Now we would like to know which one of these is the one, because both of these will produce y. Remember that we have an equation that says x equals 10 minus y, right? So, no, these are y's, sorry. They're not x's, these are y's. So x is equal to 10 minus y. When you plug in the first y, you get x equals 10 minus 10. Well, that's going to give you 0. So that's garbage. But the other x, when you plug in 10/3, you get 10 minus 10/3, which is 20/3. So there we go. 20/3 and 10/3 as x and a y. Well, here, xy equals to give us what we wanted. When you add them, you do get 10, right? Do what?
It makes significantly more sense finding all that shopping list stuff.
I mean, they both make sense. This just doesn't. It doesn't take 30 minutes at a time.
You don't have 80 billion steps to do it.
Should be. All right, so let's see. Max area. So find dimensions of a rectangle with max area with perimeter $20. This is a straight geometry problem. All we do is we say what? What's the perimeter of the rectangle? What's the perimeter of
2x plus 2y equals 20.
2x plus 2y equals 20? Great, you already have your constraint.
X plus y equals 10.
And then x times y equals max, right? We're looking for the max area. So x plus y equals to 10. Y is equal to 10 minus x. Plug in. It's very simple. Always you solve the constraint, you plug it into your objective function, and you got your 10 minus x times x needs to be a max. And then you have your 10x minus x squared equals a max. You unleash the derivative. X equals 5, y equals 5 as well. And we got it. So the dimensions are 5 by 5, which is a square. Which tells us something very special about squares, yeah. They are optimized rectangles. Maximum area. Now you can actually test this because you know that you can get all the different combinations, right? You can have sides to be 4, 4, 1, and 1, right? 4, 4, 1, and 1, that's 4 times. So you can play a little bit with this, with these rectangles, and prove, not prove, but see that square actually gives you the largest one. Because if you have a rectangle and this is 4 and this is 1, the perimeter over here is still, no, we need a perimeter 20, right? Yeah. So 8 and 2. Yeah. Eight times 2 is 16, 5 times 5 is 25. So this is smaller. You can always figure out. Now, what kind of problems are you expecting in terms of application? Well, these rectangle problems are famous as farmer problems. Same problem would be farmer wants to enclose a rectangular area for a pasture, and he has 1900 feet of fence. What is the maximum rectangular area or plot that he can enclose? That's the, so farmer wants to fence off. Is that a baby or a monkey?
That was me during the exam.
I can't tell. Farmer wants to fence off a rectangular area of maximum area. Rectangular area rectangular area with 1900 feet of fence. What are the dimensions of a max region? So we know it's a rectangle, right? This is identical problem like up there. I'm not going to solve it. I'm just going to tell you that, right, 2x plus 2y is equal to 1900, right? XY is a max, and the whole thing is same as above. You just have different numbers. So we just have a different number to plug in. So now you will cancel the 2 over there. You will get 90, right? 9500. No, 950. And you will plug that in and grind through, and you will get the dimensions in feet. It will be a square again, right? It has to. What's interesting is the modified farmer problems. And this is what you're expecting on exams and so on, along with business and stuff, which we will have to cover next time. So what do we have now? Now you have a river. All right, there's a river right there. Here's salmon. If the salmon goes to the left, which way the river flows? Depends on the time of the year, okay? So now look at the posture. We don't need a fence on one side. I still have the perimeter to be 1900 feet, but now I have one X and two Y's, right? And you have a river, so you don't need the fence on that side. So now your perimeter equation changes into X plus 2Y equals to 1900. Your area is still XY is a max. You still plug in and you solve. So it's the geometry that changes, but the idea of how you do the problem, one constraint, one objective equation, plug one into another derivative, you're done. Another modification. Let's say he needs 3 bins like this. Want to put rabbits, cabbage, and tiger. Put the cabbage here and rabbits in the middle to be closer to tigers. There we go. Do what?
How else are you going to feed the tigers?
Well, no, you have fence. That's why I have fence in between.
Yeah.
See that? So tigers and rabbits are on different sides. So no harm will come to cabbage because rabbits won't eat it. And then no harm will come to rabbits because tigers won't eat them. There's a fence in between. So this is how you optimize, right? All right, so what do I have now? Well, I have X, 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 Y, 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 Y. Or you can just keep one big X. Yeah, let's keep one big X. Better. Rather than dragging 6 X's for no reason. So now, how's my perimeter equation? Excellent. And what's my... Yes, same thing, xy equals max. Now if I put this xxx, then it will be 3xy, right? You see that? That's why I didn't want to. So if I had 3 bins like this, x, 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 then this side is x plus x plus x, which is 3x times y for the area. That's why I didn't keep 3 x's. Again, solve for x and y, plug in, derivative, solve, done. How about this one? Let's say no more rabbits, so now you just have cabbage and tigers.
There's a hole in the last one.
This is what happens when you don't sit or practice your calculus.
Or you have to slide the tiger.
So try to set up this one. Just equations. The principle for solving equations is always the same. Yeah, with that we can solve this one. Let's solve this one all the way.
big is this one?
Still 900, I guess.
So what is the perimeter where the fence goes now?
380.
Wait, hold on. We first let's set up the equation. So perimeter is now going to be 2x plus 2y plus x over 2 plus y over 2, right? And that's 1900.
Well, there's the fence inside too.
That's these two pieces.
Yeah, that's the X,
That's x over 2 is this piece on top and y over 2. Now this is a single y. All right, cool. So now when you, and then the x, y max is still the same, right? So what do? I have 5 halves x plus 5 halves y is 1900. What do you mean?
since they're gonna be squares, and you could just have X equal Y.
They're never squares unless it's a basic. Anytime you have modification, it ceases to be a square right away. None of the problems are the square other than the first example. All of these are going to be rectangles of some sort. All of them. Even the last one. We'll see now.
But wouldn't you have a fence where the river is?
Do what?
But wouldn't you have a fence where the river is?
Because animals are not as stupid as people.
Good answer.
All right. So now we're going to divide 1900 by 5 and multiply by 2 to get x plus y, right? So that's 3800 divided by 5. That's going to be 7 and then 6, 0. Is that good? And I have xy is a max. Plug that in. So we have xy so y is equal to, so from this equation y is equal to 760 minus x. We plug that in there. So 760 minus x, everything times x, is equal to a max. 760x minus x squared is equal to 0, no, max. And then we differentiate. So 760 minus 2x is equal to 0. 2x equals 760. And then x is equal to 380. No. Yeah, 380. Feet. And the y is also, wow, this is a square, this one. So this one is a square. Looks like this. This is 380. This is 380. And this is 190. And this is 190. Huh. Interesting. The previous 3 examples will be the river, and they will be rectangles. Maybe I should separate these examples with a line. There are a lot of these. We still have to do business, and then so we have a minimum cost, shortest letter, shipping crates, walking or swimming, minimum distances with a distance formula. So there's a lot of cool stuff too. And then flower garden is a cool one. That's another part that I might well, we'll talk about it next time. So there will be a part 2 of this stream. So see you all in a week.